Here is the training procedure used to train generative adversarial networks. First, you need to choose a prior distribution PZ on latent variables. Initialize the parameters of the discriminator and the parameters of the generator, and set the parameters of the optimization procedure, here a stochastic gradient descent ascent, the learning rate eta, and the mini-batch size m. Then the first step is to optimize the discriminator. To this aim, you sample m latent variables z1 until zm from the prior pz. You also sample m observations x1 until xm from the original distribution. Then you use these two samples to compute an empirical version of the value function v that you want to maximize, and you update the parameters of the discriminator using a stochastic gradient ascent step. The second step is to optimize the generator. To this aim, you sample m latent variables z1 until zm from the prior pz. Then you use these observations to compute an empirical version of the value function that you want to minimize and update the parameters theta g by doing a stochastic gradient descent step. The whole procedure works by repeating these two steps until convergence. You can, of course, use any version of the stochastic gradient descent. For example, the authors of the original paper on GANs used stochastic gradient descent with momentum. To understand better how GANs work, the definition of the KL divergence is useful. This divergence appears when we rewrote the value function. We have used before the following property of the KL divergence. It is non-negative and is equal to 0 if and only if the two densities are equal almost everywhere. We can define the Jensen-Shannon divergence, which is related to the KL divergence and is defined as in equation 122. A nice property of the Jensen-Shannon divergence is that it is symmetric, which was not the case for the KL divergence. Indeed, by definition, the Jensen-Shannon divergence is a symmetrization of the KL divergence. Besides, it satisfies the inequality 123. The Jensen-Shannon divergence naturally appears in GANs. Indeed, you can rewrite the maximization of the value function, the function Cg, as minus log 4 plus a term involving the Jensen-Shannon divergence between the density of the original data and the density of the fake data. You can now try to prove the previous properties on the KL divergence and the Jensen-Shannon divergence. You can pause the video. The definition of the KL divergence gives the first equality, and elementary properties of the logarithm gives the second one. Then, by applying the Jensen's inequality, this quantity can be lower bounded by the logarithm of an integral, which equals 1, because Q is a probability density. This proves the first statement. Now, the Jensen inequality is an inequality if and only if the function is linear or the random variable is degenerated almost everywhere. Here, the function minus log is not linear, so the equality occurs when the random variable is degenerated, that is, if Q equal alpha p for some constant alpha. However, since P and Q are probability densities, alpha must be equal to 1, which implies P equal Q. This proves the second statement on the KL divergence. Regarding the Jensen-Shannon divergence, its non-negativity results directly from the non-negativity of the KL divergence. Besides, by definition, one has equation 127, and elementary calculations lead to the desired conclusion. As mentioned before, the KL divergence is not symmetric in general, whereas the Jensen-Shannon divergence is. Therefore, the Jensen-Shannon divergence is more suited for measuring how far away two distributions are from each other. Note the following important phenomenon for the KL divergence. If Px is very small and Qx is very large, then the term inside the integral in the KL divergence of P and Q is very small. However, in this case, the two densities are far from each other. It means that the distance between two densities may not be well measured if one of the two densities is very small. You can see that this is not the case with the Jensen-Shannon divergence. Indeed, in the previous case, the term in KLPQ is small, but the term in KLQP is large. Consequently, in the case where Px is small and Qx is large, the Jensen-Shannon divergence is large, whereas the KL divergence between P and Q is small. This difference may explain why GAN have a good performance. They use the Jensen-Shannon divergence, whereas more classical estimates, such as the MLE, are based on the KL divergence. Here are some comments on GAN training. The training process for GANs is known to be slow and unstable. They are thus difficult to train. Consider a perfect discriminator that is d of x equal 1 if x is generated from the true distribution, and d of x equals 0 if x comes from the generator. Then the loss of the discriminator is 0. Hence, the gradient descent step for the generator is useless. This means that if the discriminator is perfect, it is impossible to train the generator. On the other hand, if the discriminator is not good enough, the generator cannot learn to approximate the true data distribution. So the discriminator must be good, but not too good, otherwise it is impossible to train the generator. In practice, as you can imagine, this good but not too good property is hard to satisfy. Besides, a major problem with GAN is the mode collapse phenomenon. It corresponds to the case where the generator outputs are very similar to each other and not representative of the true distribution of the data, which may be more diverse. You can see that on the bottom right picture, where you have images produced by GAN. You can see that several of them are identical and also very different from the true data on the left. You can look at more complicated techniques to circumvent this problem of mode collapse. One way is to look at Wasserstein GANs, which consider different losses to train the generator and the discriminator. You can also look at the paper below to see how you can improve GANs. To address mode collapse, you can use feature matching, where instead of directly maximizing the output of the discriminator, the new objective enforces the generator to create data that matches the statistics of the true data. Here, the intermediate statistics is the expected value of the features on an intermediate layer of the discriminator. Thus, you force the data produced by the generator to be close to the true data, at least for some pre-specified statistics. You can also use mini-batch discrimination, that is, computing statistics over the whole mini-batch and allow the discriminator to use that information to make an estimation. Since the discriminator is able to use this information, it will force the generator to produce data whose statistics match the statistics inside the mini-batch composed of the true data. You can also use various techniques such as historical averaging, one-sided label smoothing, and virtual batch normalization. You can see all these techniques in the paper on the previous slide. To conclude this last lecture on generative modeling, you can use variational autoencoders and generative adversarial networks to generate new data whose distribution matches the distribution of the true data. Both approaches are based on neural networks, backpropagation, and gradient descent, so you can use the whole toolbox of gradient descent to solve the corresponding optimization problems. The gradient flow in GAN requires that the data output by the generator are continuous. Therefore, GAN cannot model discrete data. Indeed, if the data produced by the generator in GANs were discrete, it would be impossible to pass the gradient flow through the generator. On the other hand, the gradient flow in VAE requires that the data outputs by the encoder are continuous. Therefore, latent variables in VAE cannot be discrete. Indeed, as we've seen for variational autoencoders, the latent variables are usually assumed to be Gaussian or uniform. We also needed to use a trick in order to rewrite these random variables to be able to backpropagate the gradient flow inside the network. You can look at the following references to obtain additional details on GANs. In the slides, you can find some applications of VAE and GANs. I encourage you to go through it. Several of these applications are very interesting, at least from the methodological point of view. This was the last video. I hope you enjoyed this course. Don't hesitate to put some comments or questions in the forum. Thank you for watching this course.